Hey, good evening. Good evening, everyone. Going to give it a few minutes, just to give everyone time to get logged in, and we'll get started with the next lab. I'll give a few minutes to address if there's any lingering questions for the previous lab. Then tonight, I'm going to jump in with covering some of the theory behind this one, things you need to be aware of, and just to help you get started. So tonight, the first night will be focused on the preliminary calculations and getting your PSpice schematics set up and simulations going. Let's see, it's 6:02 right now. I see 9 participants. I'm going to wait. I'll give it 2 more minutes till 6:04, then we'll kick things off and get started. I see we've got 10 on at 6:04. Let's go ahead and kick things off. So prior to jumping into this lab, I had a few questions about the report on the previous one. All I want to say is this. The report format is pretty loose for the most part. What I'm really looking for is a couple of things. One, just to see if you picked up on the key knowledge points in the lab, which are either addressed through screen capture of some of your simulations, which also doubles as like evidence that you did the work. Then the other thing is the items, conclusion items 1 through 3, just answering those directly. There's questions about like captions on photos and plots and things of that nature. If you include them, great. If not, you know, I got a pretty good feeling what the lab is, obviously, so I can, you know, make out what's what in the report, so I'm not too concerned with that. The other thing I want to address was I know a few students had some tech issues with their circuits or their analog discovery kits, and as expected on the first lab, there's a little bit of a struggle and learning curve that's anticipated with, you know, setting up a circuit and taking the measurements for the first time. Those of you that encountered that and you communicated with me, and a few of you I had a Zoom with to, you know, attempt to resolve some of the issues, you will, you know, not be docked for points as a result of that. That's what we're here for, to help each other and knowledge gained. And for some reason, if some major catastrophe occurred for some reason, and you gave it your best, that's what really matters. The key thing is you're going to walk away with the majority of knowledge that you should have gained from doing the lab. Some of you are going to struggle more than others. As long as that's communicated or even documented in your report, if you state that, like, hey, I built this up and this is what I saw and I'm still struggling with it, that's fine. At least you're telling me you're doing the work, and it kind of gives me some keys on where to help out with. So on that note, lab reports were due this evening. I did receive a couple of emails that were sent directly to me, which is fine. You'll get credit for those of you that did. I just strongly encourage you in the future to use the Moodle submission and drop them in there. It just makes grading and record keeping a little bit easier. So before I transition into tonight's lab, I was going to ask, are there any questions before we do so? The submission box isn't there. They're due this evening. Honestly though, so here's the deal. I'm telling everybody to get them turned in, and I'm going to go to the submission right now. So lab 3 conclusions report. So first question is, does this show up? Can you see this on your middle page? Do you see this link right here? Not seeing a response yet. So
Yeah,
I'm going to click on that. Great. I'm like, it's not working. Let's see here. All right, that's good. Okay, yeah, but there was no submission tag for me. Okay, hey, we'll get to the report date in a minute. So here's the real deal. I've set the due date on all these labs to be at the end of the semester, finals week, okay? The reason I did that is because I anticipate that there's going to be unforeseen circumstances to where people are going to like fall behind, something's going to happen, maybe worst case, hopefully this doesn't happen, but someone gets really sick. So I'm affording the opportunity to submit these by December 15th, worst case, okay? The reason I'm pushing you to get them turned in as we progress through these labs is because you're going to forget this information as you progress along. So I just want you to stay on top of it. The page says from, all right, yeah, I'll have to address that, okay? Okay, if you can't submit it, maybe you didn't enroll on the Moodle page. Maybe you have access to it, but you didn't add it or enroll. So I would check on that to make sure that I don't want to click on submissions right now because it's going to show other, well, let's see. So I can come in here right now and I can tell you that I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 students listed here. I think we're missing one.
It all says no submission though, so nobody's actually submitted.
Laura. Okay, let me go back, see if you're listed here. Yeah, you're listed right here. Huh. Wonder why it's not populating. We had this issue last semester too, that some students, for some reason, the link wasn't there. Let's see. I'll tell you what, do me a favor, maybe help me troubleshoot this if you can.
If I may, Professor, I actually looked at the other labs
so
that had submission tags.
Go to this part of the page, and I assume that you can see this link right here, right? Then if you can, click on the lab 3 submissions. So let's see, no one submitted it. Has anyone attempted to submit it through Moodle? Does anyone think they've been successful at doing so? I can't see the submit button either. Okay.
Yeah, we can't see any submit button at all.
Huh. Yeah, so why it should
Ryan,
be,
hello, can you hear me,
can
Professor?
drag and drop files here to add them.
Hello, can you hear me?
Yeah, file submissions, accepted file types. I wonder if I got this. Here, let me do this. All file types. Wonder if that'll work.
Yeah, we were able to hear you.
Go to submission settings. Require students to click the submit button. I don't know. I'll change it to yes. See if that helps. Okay. All right, let me come back. Seems like there's a lot of activity right here, right now. I can't hear you. Huh. Speakers. Yeah. Turned all the way up. Let's see here. So you can unmute yourselves, right, when you're trying to talk?
Yeah.
Yes.
Can you still hear us, or can you not hear us still?
Can you hear us?
All right, hold on, Andrew. Let me come down here. All right, go ahead, Andrew, and talk.
Can you hear me?
Huh.
Can't hear me?
Okay, there's
I can hear
maybe
you.
something wrong with the Zoom session.
Yeah,
I
I
can hear
think he's
We're
the
gonna have
only
to
one
dig
that can't
into
hear
that.
us.
Let me check my audio, maybe. Microphone, speaker.
Hey Google.
All right, can you hear me?
Yeah, can you hear us?
Can you hear us?
Okay. Yeah, I can hear you over my phone now.
Okay, yeah, I'm looking at the email right now and it shows 1017, but when you clicked on the cog and go to edit settings, you were able to change the date from November 23rd to a different day, like earlier, so we can submit.
All right, let me go back to the class page. We'll get this worked out real quick. Okay, so introduction op amps. Yeah, I said 10-8, but we've kicked this lab out. So what really matters is the conclusion report. So the due date, I typed it in there. Let me go back to the cog here. At settings.
Now, if you scroll down a little bit, it will show the dates right there.
Yeah.
Allow submissions.
Oh, that's why. Okay, it's not even turned on right now. Yeah. Okay. Let me do that. We'll go 15 October 2020. Let's make this 1800. Good catch. Okay. Save and return to course. All right. See if that works for you now.
It works now.
Okay. Yeah, so they're not due tonight then. I'll give you guys a little bit of break. Like I said before, I'd prefer that you get them in by like Sunday, the latest. And the reason I'm asking that is, here's the deal. I want to get them graded as you go through each step of the lab. But for some reason, if you slip on one of them and you get it into me like 2 weeks from now because of unforeseen circumstances, I'll grade it then and you won't be docked for it being late. What I'm trying to emphasize here is that I'm offering flexibility because of the circumstances, but at the same time, I'm going to put pressure on you guys to like stay on track and get things turned in as we progress through the different labs. And yeah, I apologize for that. There's still a bunch of like weird dates in here and everything, and a lot of it has to do with like the schedule just keeps flexing. Yeah, I apologize. Like I see that up here, like coming back to this op amp. Yeah, it's calling out like we would have finished it last week and turned it all in. So, all right. The key thing is don't stress. Your grade's not going to suffer as a result of it. There's just we're up against, right, as we try to like navigate all this, doing it virtually. So I appreciate everyone giving me feedback and communicating, and we'll get this resolved and keep working forward. Okay, so now that we got the lab submission part of it taken out, how's everybody at the previous lab? Was everybody able to finish it? I know I received a couple of reports via email, so I know those students wrapped them up. So I guess the key question is, are there any obstacles that anyone's up against right now that's just you can't get past on that lab? All right. So I'm not seeing any no's or any questions popping up. So I'm going to assume everyone's good then at this point, and let's transition to the next lab. All right, so we just wrapped up introduction to op amps, and you did 2 op amps on that one, right? 2 gain stages. You did a inverting and a non-inverting gain stage. And you did it with dual supplies, -5 volts and +5 volts. This lab, there's going to be some noticeable differences. What is going on with my computer right now? Did I lose? No, I'm still connected. Huh. Hold on real quick. Close this out. All right, here we go. So there's going to be some noticeable differences. The first one is right in the title, right? It is a single supply op amp. So why is that of interest? Well, a lot of times, think of something as simple as like, I don't know, like your remote control for your TV, right? Like maybe it has a couple of AA batteries, AAA batteries in it. So more than likely, it's going to have a single supply on it, like maybe a 3.3 volt, supply, or a 5 volt supply, or whatever the DC is, and it gets regulated down. So you're not going to have that negative supply available. So most circuits now operate off of a single source, like a lithium ion battery maybe. Then it goes to a power management system and it creates a bunch of DC supplies for you. The majority of those circuits now operate off of like a positive DC supply. So for this op amp, the key difference here is pin 7 is still going to be your positive supply, your VCC. Pin 4, instead of being negative VCC, now it's going to be ground. So now you're going to be going from 0 volts to 5 volts. So some of the limitations that might hit you right off the bat is you just lost half your signal swing, right? Or some people call that dynamic range, like the dynamic range of your input and your output. So previously, theoretically, you could swing between the limits of -5 and +5. Now you're only going to be able to go between ground and 5 volts. All right, so that's the first thing.
The next thing is your biasing and feedback network is a little bit more complicated in the circuit. Now, don't get scared away. I'm going to walk you through it right now. So I recommend you read all the background up here. A lot of it kind of like touches on what we just talked about. What I'm going to ask for you on this lab is spend this week working on the preliminary calculations. So steps 1, 2, 3, 4. So that's all your hand calculations. Then build up your circuit. And I'm going to talk about this figure 2 here in a little bit. We'll get to that. But then I want you to do steps 5, 6, and 7. And the reason we're going to talk about this is because this is one like slight variant in terms of how you're going to simulate the circuit compared to how you're actually going to build it and take measurements. Okay, so let's go back up to the top. Let's see here. So first of all, one thing I want to point out with figure 1 is all you're being shown right now is the biasing in the feedback network. There is a VN labeled right here, but what you're not seeing is, and that kind of goes back to figure 2, you're going to capacitively couple a signal into VN right here. So you're going to have another capacitor between VN. I'll scroll right back down so you see that. So see this VN right here on figure 2. So you're going to have your function generator. That's what VS is. And it's going to go through CN. Then that CN on the other side is going to tie into VN right here. Okay. So prior to that, let's talk about a couple of things. We have our feedback network, which V out through R2. And it should always be going to your negative terminal, right? Negative feedback coming around your amplifier. You got R1. Then you got this 10 microfarad capacitor to ground, right? Then on the positive terminal, you have this 22 kilo ohm resistor, RB. Then it's going to this node called VREF. Then it's going to, if you're not familiar with it, this 3-terminal device right here is a potentiometer. So you got your 2 terminals like a standard resistor. Then you got, this is called a wiper in the middle. All right, so let's talk about the bias part of the circuit first. The whole point of RP and RB is to set a DC potential at VN right here, okay? So what you're gonna have here is this VCC down here on your potentiometer is the same VCC, 5-volt supply, that's supplying your op amp. What you're gonna do is you're gonna, potentiometer will have like a little screw on it, and you'll have like a little, you know, like almost like a jeweler's screwdriver in your kit, little flathead screwdriver, and you're going to turn that knob, and this wiper is going to go up and down, and you're going to set this resistor right here is acting as a voltage divider, okay? And you're going to set the voltage right here to be VREF at a particular point. So that's going to set your DC bias. So let's talk about that real quick. First of all, are VN going to be the same DC wise? Hopefully you're saying yes to yourself right now. And the reason being is current can only flow between VCC and ground. The reason current cannot flow through the wiper and up through RB is because this is an ideal op amp, right? And current can't flow into the input of an op amp. So if current can't flow between the wiper through VREF up through RB to VN, then by Ohm's law, if there's no current drop across this 22 kilo ohm resistor, then N and VREF must be the same value, right? They are. Okay, so that's what's used to set your voltage coming in. And we're going to come back to this potentiometer in a minute. We're going to talk about that a little bit more because one of the questions down here has you do a little thought experiment on that. All right, the next thing is you're going to have a feedback network with a capacitor in it. So a little bit different than your past circuits, right? Because what do capacitors do at DC? They act as opens. So it's blocking any current coming around its feedback network, right? At DC. That's the key point. Reason I say that is because you're going to see in a minute that you can look at this circuit two different ways. You can look at it from a DC perspective, then you can look at it from an in-band perspective. So you're soon going to see this is a mid-band gain amplifier. Unfortunately, I wasn't able to draw up a chart quick enough. Maybe I'll be able to simulate it here in a little bit. But what it means by mid-band is, hopefully you're familiar with like what the pass band chart looks for, like a bandpass filter. So it's going to reject signals, say from like DC up to like a kilohertz, right? Then it's going to pass signals from like, say, a kilohertz to 100 kilohertz. Then it's going to reject signals above 100 kilohertz. That's what this op amp is doing, the way this gain stage is set up. Not those frequency values, but in terms of, you know, plot behavior, that's what it's doing. Why is it doing that? You might be asking yourself. Well, first of all, you're going to have that capacitor right here, right? And I wish I would have drawn it up here, but you're going to have this one right here feeding a signal in here. Well, first of all, in order to get a signal across that capacitor and coming into VN, it's got to be high enough frequency, right? In order for the signal to couple through the capacitor. So really what we're thinking about here is, at what frequency, well, let me rephrase it. First of all, the impedance of a capacitor is a function of the frequency, right? So it's like 1 over 2 pi FC. So it's impedance is 0. So really what we're looking at is, at what frequency does this capacitor, think of it as a switch, behave as closed, okay? So you got the capacitor coming into the circuit. The frequency has to be high enough to where that capacitor is closed and you're coupling the signal coming in. Then the other condition that has to exist is in your feedback network. The frequency has to be high enough such that this capacitor acts as a closed switch across here, right here, right? And by closed switch, what I really mean is that the impedance of the capacitor at a given frequency is negligible compared to these other resistor values, okay? That's often referred to like going above and below that, like the pole frequency is typically a defining moment, or a metric for that, I should say. So at DC, we've already established that like VREF is going to be the same as VN, right? Well, what about the rest of your op amp? What's happening at DC? Well, our feedback loop, we could just completely forget about R1 and the capacitor, right? Because no current's going to flow from V2 to ground because of the cap. What about R2? Well, yeah, you're definitely going to have a voltage on the output on V out, but what's the voltage going to be at V out and V2? There's a couple different ways to look at it. One of them is you can recognize that this is a non-inverting amplifier, right? Because you're applying the input to the positive pin. So the gain equation for a non-inverting amplifier is 1 plus R2 over R1. So we got 1 plus R2, and we'll call it R2 for right now, over R1. Well, R1 really isn't just R1 the resistor, it's R1 plus 10 microfarads. So at DC, this capacitor is infinity. So it's 1 plus R2 over infinity. So what's the gain? It's 1. So you might not see this right off the bat. It might not be evident, but think about it. Your only feedback network is from V out through R2 to V2 back to this terminal, right? That looks pretty close to like a buffer, right? Just having a wire coming back and around right here instead of resistor. But the key difference is you have a resistor in the feedback loop. But you got to keep in mind, there's no current going into the negative terminal on this op amp. So therefore, whatever V out is, V2 is, right? So we've already established that the gain is 1 at DC because R1 is effectively open. We've also established that there's no current going through R2. So the circuit is acting as a unity gain buffer. So let's go back to the very beginning. Whatever Vref is, Vin is, and whatever Vin is, Vout is, and whatever Vout is, V2 is. So all these voltages right here from Vref, Vin, Vout, and V2, they're all the same. Assuming on one condition, that Vn is a large enough voltage to where this, and by large enough, it's got to be between 0 and 5 volts, right? Well, the reality is it won't work at 0 volts going all the way down. There's got to be enough of a bias on the input to get it to work. I encourage you to look at the data sheet or just play around with it through simulations and measurements. But what you're probably going to find out is that any voltage at Vn, if you set Vref, which is effectively Vn DC wise, if it's a lower than I think about 1.2 volts, right around there, the circuit won't work. It won't bias upright. Then you'll see your output rail out. Okay, so we talked about the biasing, the capacitively coupling the signal coming in, and the capacitor and the feedback network. Through these steps really quick here. So RP is, we're talking about step 1 here, is a potentiometer. They want you to choose between 5K and 25K. I don't have my kit in front of me right now. I know there's potentiometers in there, so there should be one in this range. Go ahead and pick that. For the capacitors, I mailed some 10 microfarad capacitors, so just use the 10 microfarad capacitor here and another 10 microfarad capacitor here to couple the signal in when you get to that point. Let's see here. So under the assumption that a 10 microfarad capacitor is an AC short circuit, so the frequency is high enough, this is shorted out. Select R1 and R2 to get the gain of the amplifier between 30 and 45. Then I give you this equation. So you got two unknowns, R1 and R2, and you have two conditions. The gain's got to be between 30 and 45. So 1 plus R2 over R1 has to be between 30 and 45. Then R1 plus R2 has to be between these values. Keep in mind, you've got to be using kilo ohm resistors on here, right? Because you want to minimize the current coming around the feedback loop. If you're using like single digit ohm resistors, there's going to be too much current coming around it. It's not going to work. So you're just selecting your R1 and your R2 values to get everything to work, right? Let's see here. Next one, at what frequency is the reactance to the 10 microfarad capacitor equal in magnitude to the resistance of R1? Call this frequency FP1. So that is just going to be 1 over, let's see here, 1 over 2 pi FC. So 1 over 2 pi F 10 microfarads is going to equal R1. Then you're going to solve for frequency. So that's step 2. Let's see, step 3, assuming the operational amplifier is ideal if Vref equals 5 volts. All right, so let's get in front of that right now because this lab was written up for using a 10 volt supply. So set Vref equal to, let's do probably 2.5 volts. We'll just go right in the middle for right now. So do 2.5. So then it asks you, what are the DC voltages Vout and V2? Hint, there's any DC current. So I just talked to you about that, right? So that was your hint right there. Kind of already gave the answer away. Okay, step 4, later in the experiment, an AC signal will be connected to Vn. So right here. This step checks the input resistance at that node. Assuming the operational amplifier's input resistance is infinite, so just looking into the op amp, it's infinite. What they're asking you for now is, what's the resistance seen looking down, right? So if you were standing at Vn and you were looking down, what impedance would you see? And this is kind of the trick question here, what I was getting to. Assuming that the operational amplifier's input resistance and highest small signal resistances. That's your key right there. Small signal resistances seen to the ground from VN. Hint, the resistance looking into the potentiometer depends on its position. Okay, so let's come back up to that. That's a true statement. So your impedance from VN seen looking down into here is going to be RB. So it's always going to be, here's going to be your equation. It's going to be VN equals RB plus this. This is going to be a parallel resistor. And I'm going to show you on a schematic. I'm going to jump to that right now. So let me go to this. I've redrawn it for you. So you're going to come down through VN. You're going to have your 22K ohm. Then your potentiometer, VREF is your wiper right here, okay? I've split it into two. I'm assuming I have a 10K potentiometer. So it's 10K from this terminal to this terminal. And I've drawn it right now with the wiper right in the middle. So I got 5K on top and 5K on bottom. So for a small signal seen looking into this, keep in mind, small signal power supplies are constant, right? So they look like a ground, just like here. So really, from a small signal perspective, it's RP top and parallel with RP bottom. So the question on number 4 for your hand calculations is, at what wiper position does the maximum impedance occur? And at what wiper position does the minimum impedance occur? So I like to think of this in terms of boundary conditions, all right? There's a couple different places this wiper could go in terms of extremes, right? So right now we got it in the middle. It could go to the very top to where RP top is, or all the resistance is, or the wiper is all the way up at VDD. Or you could put the wiper all the way down at ground. Well, let's start with the first one. If the wiper is right in the middle, you're going to have your 22K plus these two resistors in parallel. So 5K times 5K over 5K plus 5K. And what we already know is if it's equal resistances, the parallel combination is half of one of them, right? So it's going to be 2.5K. So your impedance seen looking down would be 22K plus 2.5K for a 10K ohm pot. Now, if you got like a 15K or 20K ohm pot, you need to scale it accordingly. All right, so let's talk about the extreme conditions now. What if your wiper is all the way up at VDD? Well, now RP top is 0. So you have 0 in parallel with 5K. Well, what's 0? You know, parallel resistance, fundamental rule of thumb, it's always going to be the lowest value, right? Or less. So if it's 0, so 0 times anything is 0. So at VDD, it's just 22K plus 0. If the wiper goes all the way down to the ground, same thing. It's just 22K plus 0. So right there, you know your upper and your lower impedance value bounds if you're looking down through here, because this impedance is going to be a function of the resistance coming down here, right? Why is that important? Okay, I'm going to shift this down. Hopefully this works for me, because I want to show you one more thing, because you have one more calculation, one more pole frequency that they ask you about, right? I want to draw that one in here for you. All right. Let's see here. Okay. So here's how you're going to couple your signal in. You're going to have this 10K here, and latencies on this is horrible. Okay. Place, PSpice component, source, control voltage. I like using the sign because it's got all the options. Let's see here. Actually, I don't want 1,000 volts for an amplitude. I just want one. Okay, 1K. We'll set AC to 1. Okay, so now we have a complete circuit now. Okay, so the way I have it drawn right now, this is your potentiometer, your RP top and RP bottom. I got the wipers set right in the middle. So that's going to give us 2.5 volts here on VREF, 2.5 volts on VN. Then we'll have 2.5 volts on V out and 2.5 volts on V2. Here's our function generator right here. We're capacitively coupling a signal coming in, right? What's the pole frequency? So the pole frequency kind of tells us like at what frequency do we need to be above in order to get the circuit to perform right. And you have two conditions, right? You have this pole frequency and you have this pole frequency. So this one up here is easy. It's just 2. This one's a little more complicated because you got the 22K ohm and the potentiometer. That's why we simplified it and we figured out what the impedance is looking down through VN. So remember, they're asking you at what frequency does they're going to ask you, does C2's impedance equal the impedance seen looking down? So that equation is going to be very similar to the one up top. It's going to be 1 over 2 pi C2, so 1 over 2 pi, 10 microfarads, equals this impedance looking down, right? So the impedance looking down, there's 2 impedances that you could work off of, right? You could work off of the minimum or the maximum. Which one do you want to choose? Well, you know, I'll draw these out. I'm going to put them in the slides for you with the equations, and I'll post it on the page. But there's an inverse relationship between frequency and impedance, right? In this equation, because it's 1 over 2 pi FC equals a resistance. So really it's F equals 1 over 2 pi RC, right? So the lower the R is, the higher F is. So that's why they have you calculate the minimum. So you know that's like your worst case condition, right? If this wiper is at VDD, then your frequency needs to at least be above that in order to get everything to work. So that's just kind of like a rule of thumb for you to work off of. All right, so we got all this drawn up. I'll tell you, I'm going to change these really quick. I think they wanted the gain of the circuit to be like 30 to 45. I'm just going to leave this as 30K and 1K. I'm going to save. I'm going to do a quick simulation because I just wanted to show you a few things. So this is lab 4. Let's see here. Did it take? Oh yeah, got to hit the icon on the bottom. Let's go with this. I'm going to do, the first one I'm going to do an AC sweep. I'm going to go from 1 to, let's do like 10 meg, like 1,000 points per decade. Let's see here. I'm going to put one on the output. I'm going to put one here. And yeah, I think that's good. All right, so yeah, it's your signal being coupled in. Actually, no, I'm going to do one more. Then I'm going to do one down here just to illustrate something. I'll hit that. I'm going to run it. And let's look at our plot. Open up. I need to go a little bit higher in frequency. Hold on real quick. PSpice, edit simulation profile. I'm just going to take this all the way up to 1 gig. And the reason I'm doing this, I just want to show you like what a, let's see here, where's V out? Okay, so V out is flatlined all the way across. That's not good. Let's go back and take a look at our schematic and see what's wrong right here. Why is that occurring? So we got let's see here. We got 5 volts here, 0 volts here. Why is this 928 millivolts? We got 0 here, 5 here. Let's see here. We got, yeah, this doesn't look too great. Something's not quite right. Let's see here. It might need to be a little bit higher. Let me try something real quick here. Actually, I'm just going to do this. I'm going to come in here and change this just out of curiosity to 10. Save that. And we'll run it again. Yeah, it's still not working right. Let me try this. Delete this wire real quick. No. Let's see here. Come back to DC. Come on, computer. DC. Bias point. I'll save that. Okay. Huh. I wonder if it's the way I name these resistors. Hold on. Trying to troubleshoot this on the fly with you real quick. Kind of get a feel for what's going on. Let's go to PSpice component, resistor. Sometimes they can get a little funky on the name. I tried to be creative and name them that way for you just to make it clear, but now that you know what I'm talking about, maybe we just run with this. Sure. All right. Yeah, so if you've ever seen this green circle here, that kind of indicates you that there's an error right there, and it doesn't like it. That error was a floating symbol at that point. So, okay. I'm gonna come back in here, do a place, PSpice component, resistor. Where this guy up? There we go. We'll save that. Run it again. Huh. Now let's go back to the lab real quick. There might be something with, let's see here. So recognize the purpose of the pod is to create a variable DC source. So in Spice, you do not need to use the potentiometer, but simply connect VREF to DC. Okay, so we're going to do that within the simulation. So when you build your schematic up, this is what it's going to look like with the pod, even though I split it into 2 resistors right here. So what I'm going to do, I'm going to do what they suggest for the lab. We're going to come in here, delete that. Let's see here. We're just going to have our VDD for, let's see here, place. Come on, computer. All right, here we go. replace PSpice component, PSpice ground. All right. I'm gonna name that VDD. That there. And I'm going to change this guy back to 5 volts. And let's see if I can do this. Here we go. Copy and paste this. I'm going to delete the VDD reference. Actually, I'm just going to rename that VREF. I'll put the VN one back in since I accidentally deleted that. And I'm going this back to 2.5 volts. I'm going to save it. And I'll hit run. All right. It's still not liking that. Change this to 10. Change that to 5. Kind of wondering if it's a limitation of the op amp, maybe these lower voltages. Yeah, something's. Delete this guy out for a second. Yep, that was the wrong one. So that time I had it upside down. Come on. All right, get the vertical. Oh, I see what's happening. I see my problem now. So I had it hooked up right. Classic mistake. V positive right here, V negative right here. So I'm applying the wrong voltage. So what I need to do is get rid of this VDD term here. All right. Yeah, I apologize for taking up so much of your time on that part of it, but you know, hopefully you don't make the same mistake I did now. I was about to do the same thing all over again. Okay, so pay close attention to your connectivity. Make sure you get everything wired up right. Let's see here. Then this should work now. Rename that VDD. Come over here. Okay, this is just the DC part of our circuit. Then we'll have to come back in and hook the source back up. All right, perfect. Okay, great. Now we're seeing what we want to see, right? So this is just the DC part. So you got your 10 volts here. I'm going to actually come back now, and I'm going to change this to 5. And I will change this to 2.5. So it works with your lab. I'm going to save that, run it again. Voila. Okay, so what are we seeing, right? VREF coming in, you got 2.5 here on VREF, 2.5 here, 2.5 on your output, 2.5 on your input. Golden, looking great. And you got 2.5 going through this resistor, and this capacitor is an open, right? Let me go back real quick. Okay, doesn't look like any questions are popping up. That's good. All right, so let's drop the capacitor back in. So we're going to have our 10 microfarad capacitor here. And we'll put our source back in. Let's see here, source, voltage source, sign. All right, let's go back. 0. And that doesn't really matter, right? Because we have a capacitor here. So you have DC decoupling, right? So even if you had an offset on this one, it would have no impact over here because you're through DC, you're forcing this to be at 2.5 volts. Let's see, AC1. Okay. So now we got everything hooked back up. We'll do one more DC bias point, make sure it's still good. Yep. And we'll go to PSpice, edit simulation profile. We're gonna do our AC sweep now, all the same. I need to put a few more voltage probes back in. So I'll put one here, I'm gonna put one here, and I will run this plot for you. Perfect, that's what I'm looking for, finally. All right, this is your mid-band amplifier right here. So I don't have it in dB, but you can see at some 3 dB point, you're gonna roll off and you got no gain, right? Then this is called the flat band region right here. So this is where you approximately get constant gain of, 30 or 45, whatever you got your gain set to. Mine's set to 31. Remember, I did 1 plus 30K over 1K, so that's 31. Then at a higher frequency, it's going to roll back off and fall down, okay? So you have 2 pole frequencies to calculate, going back to your schematic. I'm going to pull that up right now. Let's go back to the lab page right here. So you have the pole frequency for your feedback network, which is your 1 over 2 pi FC equals R1. Then you got your 1 over 2 pi FC equals the impedance looking down, right? So here's your general rule of thumb right here. These are each going to be, more than likely, these 2 are going to be a different frequency, okay? Let's just say one of them is like 5 kilohertz and the other one's 10 kilohertz, okay? Here's the key thing I want you to keep in mind. You have to satisfy both conditions in order to get it to work. So, and by satisfy, going back to treating these as switches, right? Like this capacitor, then the one coupling the signal in, they both have to be acting as shorts. So you got to have the one coupling the signal in, acting as a low impedance to get the signal into your amplifier. And you got to have this capacitor acting as a really low impedance or a closed switch in order to get your feedback network to work, okay? So when you calculate those 2 pole frequencies, you're going to have 2 low frequency values. You got to pick the higher of the 2. So again, like I said, one might be, say, 5K, the other one's 10K. Then usually, as a rule of thumb, you'll go like an order of magnitude above. So if it was like 10K, you would say, hey, okay, the frequency's got to at least be 100 kilohertz. I can already tell you right now, from what I recall from this lab, they're going to be really low values. So it's going to be on the order of like maybe even tens of hertz or hundreds of hertz. And then you're going to be like, it's got to at least, be operating at a kilohertz in order to get to work. So then you might be asking, well, okay, that's to get this part of it to work, to get it up and running, right? Into this flat band region. Why does it roll off up here? That's the limit of your amplifier. That's the gain bandwidth limitation of your amplifier. So one thing I could illustrate is right now, we'll just call it 10K where it's rolling off right here, right? So if I come back to the schematic and I change this to like, let's just do 1K, all right? So now we got a gain of 2, right? 1 over 1 plus 1 over 1. So what happens? So the gain's much lower, right? So I only got a gain of 2, but what happened with frequency? Now look how wide my mid-band gain region is now, right? Remember before it was rolling off at 10K? Now it's all the way up to like 100K. So I traded like a little bit more than essentially an order of magnitude of gain, right? I went from 31 to like 2, so a little less than 3.1, and I gained an order of magnitude of bandwidth. So that illustrates for you right there, just something I want to drive home, the gain bandwidth product. You can't have both. You could either have high gain and small bandwidth, or you could have low gain and wide bandwidth. So I just want to use this simulation example to kind of hit that home. All right, so that covers the preliminary calculations. For simulation, it's pretty much everything I just did right now for you, right? But you got to come up with your own resistor values, cut the voltages in half. So VREF 2.5, VCC 5 volts, okay? Then you're going to do some sweeps. You're going to calculate these impedances. You're going to do a 50 volt, millivolt peak-to-peak sine wave. And that'll conclude this week. For next week, you're going to build this circuit up on a breadboard. And the only difference is, instead of DC coupling like I did right here, your VREF through, this should really be a 22 kilo ohm resistor. I left it 1K, but that'd be your 22K right there. The difference with the breadboard is you're going to be building this circuit up with the potentiometer, then tuning the potentiometer in order to get to work, to get the bias condition you want, the VRF. Then you're going to come through here and you're going to complete some lab steps. I can tell you one of the last lab steps, they're going to tell you to remove C1 and replace it with a short circuit. This has confused some people in the past on step 13. So first of all, they don't label C1, right? So that doesn't help. I'll tell you right now, this is C1, okay? That's your feedback network. Now we're jumping ahead here, but I'm just trying to help you out in case you work ahead on your own. What do we have right now that's unique about this amplifier? You have two different types of gain, right? You have DC gain and AC gain, okay? What's our DC gain? Our DC gain is unity, right? Because this capacitor blocks the DC, okay? Our AC gain in our midband region, when both capacitors are acting as shorts, is 1 plus R2 over R1. So your circuit is going to have a gain of 30 to 45 for AC and a gain of 1 for DC. What happens when you get rid of this capacitor and short circuit this right here? What happens to your DC gain? Hopefully it just kind of clicked for you that, okay, now my DC gain is the same, right? Because there's a DC path. Now my DC gain is, say, 45, just like my AC gain. Okay, what does that do to your circuit? Well, we purposely picked VREF to be 2.5 volts. So it's right in the middle between 0 and 5 volts, DC-wise, right? So your circuit goes up and down right in the middle between 0 and 5 volts. Well, now whatever voltage you have here is getting gained up between V in and V out by 45. So in order to get V out to equal 2.5, VREF has to be 2.5 divided by your gain. So 45, or 2.5 divided by 45. That's going to be a really low number, right? I mean, we're talking maybe like 100, 150 millivolts, somewhere around there. Chances are it's not going to work. And hopefully you remember that there's a minimum input common mode range voltage this amplifier has to have in order to get to work. So I encourage you, once you get to that step, to kind of play around with it and figure out, like, what is the voltage got to be in order to get this thing to work. And chances are what you're going to find out is with the gain of 45, you can't get this voltage to be within the operating range of this amplifier on the input to get 2.5 volts on the output. So that's one of the major reasons we had this capacitor in back here is we disconnect the DC gain of the circuit. Now, why would you want to do that? I'll close on that. Well, let's imagine this is like a amplifier for audio gain, right? We can't hear DC, but we hear audio. So this would be a perfect amplifier for that, to where you could set the voltage that you want the output at, and even better, you can tune it, right? So if you want this output to be a little bit higher, the DC value, or a little bit lower, you could tune it with this pod. Then you're getting the gain within the band frequencies that you want, and you don't care about anything that's happening at DC. All right. So between this week and next week, I want everyone to work on the preliminary calculations and the SPICE simulations up through 7 at minimum. Hey, if you want to start building a circuit and working on and get this lab done even faster, by all means, do so. I encourage you. What I'll try to do, well, I can tell you what I'm going to do right now. Let me go back to the Moodle page. Let's see here if this will let me backtrack. Nope. So the reason I'm doing this is because I can tell you right now, I'm actually leaving town next week on Wednesday, and I'm going to be gone from Wednesday through the following week, and I'm not going to be in cell phone range where I'm going. So what I'm going to do is I'm going to pre-record a video for next week to close out this lab, and I'm going to do something similar to what I did on this one, kind of show you screenshots of the breadboard and get everyone clued in, like how to hook it up, what to measure. I'll even put all the equations I talked about tonight on there. And that will help you close out the single supply operational amplifiers. So there's not going to be a Moodle session live for the next 2 weeks. I'm going to be out of pocket. So I'm going to pre-record a video for you for the single supply op amp lab to cover that out. For the diode circuits, I am going to scale that lab back a little bit. I got to look at our kit and see what components we have to work with. But what I'm inclined to think and what I did last semester is I'm going to have everyone just do a 1 week PSpice based lab for the diode circuit. So I want everyone to simulate it. You don't have to build it, is what I'm going to shoot for. Then when I get back, so let me look at the calendar right here. Yeah, so I'm going to be gone. So no class, 22nd or 29 live. I'm going to pre-record a video for you to watch. So our next live class will be November 5th. I will be available for office hours earlier in the week. You know, so I'll hit you up for that if anyone needs it. Then for the, so next week on the 22nd, you're going to work to close out the 29th, you'll do the diode lab, a scaled back version on your own through simulation. I can answer questions when I get back this week. Then on November 5th, we're going to jump into the MOSFET lab and kick off there. So that's it for tonight. Any questions? Nope. All right. Well, if you don't have any questions, go ahead and sign off, get to work. And if anything comes up, post something on the Moodle page or shoot me an email.